All right. Good morning, everyone. Welcome to our first session for today. We have 4 talks, and the first one will be on automated differentiation ptychography by Sushobhan, Ghosh, Youssef, Nashed, Cossairt, and Aggelos Katsaggelos from Northwestern University and Argonne National Lab. And Sushobhan will give the talk.
Hello, good morning, and thank you for coming for this presentation on automatic differentiation ptychography. I know it's 9 a.m. in the morning, but let's see. So we present ADP, or automatic differentiation ptychography, as a fast and accurate ptychography technique. And this is the work I did alongside Youssef, Oliver, and Aggelos from Northwestern and Argonne National Laboratory. So let's talk about nanoscale imaging. So nanoscale imaging is a very important topic for a lot of different communities, and for that reason, over the past 100 years, we have come up with various different techniques to image various different objects at nanoscale. So if you see, we have techniques to image E. coli cells at like nanometer resolution, minerals and the structures at nanometers, as well as the IC chips that we make, which now have come out to be manufactured using nanometer technology. And actually, a big part of the work that we did was the motivation was to be able to image chips at less than 25 nanometer resolution, lateral resolution, that we define in this case as nanometer. Also, we are looking at transmissive geometry, or the projection of the whole 3D volume that we are imaging, because we are using X-rays to image these chips. So let's look at some of the techniques that is popular for X-ray imaging. The first is X-ray microscopy. It offers low resolution because it's limited by the aperture of the lens that we use, but you can use it to scan the whole sample, so it can be done for extended samples and at almost no computational cost. And then, on the other hand, we have coherent diffraction images, which offers higher resolution because it's not limited by the aperture of the lens, but it cannot be done for extended samples because the sample has to be smaller than the size of the probe that you're using for imaging. And also, you have to do some kind of computation to be able to retrieve reconstruct the image from the diffraction patterns. Now, X-ray ptychography comes out as the best of both worlds, where you can get high resolution as well as for extended samples, but it comes at a cost that it's very, very computationally intensive. And this is the problem we try to address in this paper, is like, how can we come up with an algorithm that's computationally efficient and also reconstruct in a reasonable amount of time? So what does the ptychography setup look like? So you have an X-ray beam that you focus at a spot on the object. In this case, the incident beam we'd call P of R, or probe. And then it's modulated by this object, which is a complex object we denote by O of R, and we collect the far field diffraction patterns at a detector, and the intensities, we'll call it I of I's. We only measure the intensities and not the phase, and the task is to be able to computationally recover both the phase and the amplitude of this sample, as well as when we see that for the probe as well. Also, we have scan positions R of I's, which are the X and Y coordinates of the position that we are scanning the object with. And so you always have, for a scan position R of I, you collect intensities I of I according to this forward model, which is object times the object at O of I. And we can do a Fourier transform because it's an approximation of the far field propagation, and the intensity is just the square of this. And the idea is to come up with a reconstruction algorithm that can take like pairs of I of I's and R of I's and reconstruct the object back O of R. But as we realize that you cannot reconstruct the object without reconstructing the probe, so the ideal algorithm would be which can reconstruct both the probe as well as the object. Also, remember I mentioned that you scan this beam across the object in a pattern, and so there are two scanning techniques basically. One is step scan, the other is fly scan. Step scan, what it does is it happens in a move, settle, and scan manner. So and the scanning and the detector is only collecting photons while the beam is settled at one position. And you see these colored regions are where the photons are collected, and these white regions are where the probe is actually moving and settling, and so we do not collect any photons. On the other hand, fly scan is a technique where you collect the photons as the probe is moving across the fly area, and so you do not have these move and settle times, and that makes fly scan a lot faster than step scan. But the disadvantages are that now these algorithms that we develop need to account for this kind of a motion blur that we introduce while scanning, and that also is computationally intensive. So if you look at this image on the left, you have the diffraction pattern as you'd collect in a step scan, and you can clearly see the speckle patterns here are very distinct. But when you look at the diffraction patterns in fly scan, you see that the speckle patterns are more or less like kind of averaged over the fly area. Now let's talk about some of the current methods to reconstruct from ptychography data. So Maiden et al. Came up with an algorithm, an iterative algorithm that updates both the object and the probe iteratively by calculating the gradients of this error function. And the error function is simple. You have the object times probe Fourier transformed magnitude subtracted by the measured intensities for that particular patch, square root, and you take an L2 norm, and then you try to find the grade. You try to make updates to the object depending on the gradient with respect to the object. This is simple gradient descent on the cast function, and they showed that this can recover both the object and the probe simultaneously. Also, Deng et al. Then came up with a implementation of EPI that works for fly scan as well. So what they do is it's a simple trick where instead of reconstructing just one probe for the object, you have multiple probe reconstructions, and the idea is that this added degree of freedom in the number of probes can model the different fly position that the incoherent sum that happens in the fly positions. And the update rules are simple. Again, you have the cost function, you make the gradient updates to the object in the probe. And if you talk about the advantages, again, they have an extra degree of freedom, and they hope that that models the fly motion of the beam. But the disadvantages are that now you are assuming that for every patch, the motion of the beam across the patch was in the same direction. Also, this is not a very accurate physical model of the problem, because if you look at the reconstructed probes, first of all, they should be technically only one probe, but you reconstruct multiple probes, and they look nothing like what a probe would look like if you had just one probe. Although they say that the footprint, if you sum them up, the footprint of this probe would look similar as if the probe moved across the fly area in the time that it was recording. Okay, so far we have talked about the EPI algorithms, and then Nashed et al. Came up with the idea that we can use the same error function, but instead of calculating the explicit function for the gradients, why not have TensorFlow calculate the gradients for us and make the updates to the object? And they show that since they power the leverage of the gradient descent optimizers, in this case Adam, and a GPU which is optimized due to the TensorFlow framework, they can actually get a better accuracy in the reconstruction or a lower reconstruction error. In this case, the blue and the red are the AD algorithms, and green and yellow are the pi algorithms, and it worked well. But some of the major disadvantages that the technique had was, first, it only worked for in the case where they know the ground truth probe beforehand, but in reality, in real experiments, they don't exactly know what the probe beam is, or because the probe beam keeps changing due to drift all the time. Also, if you see, the initial convergence is very slow. So if you were to if you want to have a technique which is limited by time, you cut it off somewhere here, and then you are actually worse than you would have for the pi algorithm. Also, they do not present a technique to do fly scan, so this only works for step scan. So before I talk about our techniques, I would like to present what the two metrics are that we're going to test our algorithms on. First is the acquisition speed. So scan time is very important because, as you can see, if you try to like image 1 millimeter square area, step scan actually takes like 342 hours, whereas fly scan takes 3 hours. So we definitely want to have an algorithm that works in the fly scan regime than in the step scan regime. Saves a couple of orders of magnitude of time. Also, accuracy, which we define as the reconstruction accuracy you can get within a time frame. So we are not looking at what the results would be at, like, if you give it infinite amount of time, but like within a given time frame. The reason is that when we are collecting these diffraction patterns, these are coming out at like almost like 3 kilohertz, and you do not want to have to save all these diffraction patterns in memory before starting to reconstruct. You want to reconstruct on the fly, and for that you need algorithms that converge really fast. Okay, so for comparison, let's put these algorithms that we discussed in a plot where one dimension is the acquisition speed and the other is accuracy, and we see that ePy, since it's step scan, it lies in the low acquisition speed regime. Also, it has lower accuracy compared to the other algorithm we talk about. Also, the multi-mode ePy, which models the fly scan, so it's faster, but it achieves the same accuracy as that of ePy. Then we talked about Youssef's step scan ADP, which again gets better accuracy than ePy, but I have only given half a block to it because it's not a complete algorithm, and you need to be able to retrieve probe as well to make it, to call it a complete algorithm. So we did that. We went ahead and implemented a step scan ADP with probe retrieval, and how we did that was take the same error function, but now we create this computational graph in TensorFlow where you have the object and the scan positions R's, and then you obtain a slice of that object, multiply it with a probe, which is now a variable, and then calculate the waveform, do a forward propagation, take the magnitude of intensities, and subtract it from the measured intensities, and do L2 norm. Then we allow the TensorFlow backpropagation algorithm to calculate the necessary gradients that it would for the object as well as the probe. Now, this sounds very trivial because we did not do anything other than just declaring the probe as a variable, but the challenges that you introduce is now you are trying to retrieve both the object and the probe, which are now doing element-wise multiplication. And so there is this inherent ambiguity in because there are multiple solutions to the same to probe an object that would give the same psi of I, right? So the gradient descent would not know which one is a better solution, and hence your object might not look exactly what the object actually is. So what we need is a better probe initialization. And so what we did was a very rough estimate of the probe initialization is take the square root of the intensities and then just mean them. Since the probe is constant throughout the whole acquisition, we assume that this averages out the signal from the object, and an inverse Fourier transform gives you at least the amplitudes of the correct amplitudes of the probe for initialization. This is not a perfect initialization, but it gives you a starting point from which you can recover. Also, we only start reconstructing the probe after we have converged reconstructing the object without probe retrieval. So what does it look like? So in this graph, you can see that the blue lines are the pi algorithms, and the red ones are the AD algorithms. The dashed ones are without probe retrieval, and the solid ones are with probe retrieval. And you can see that once you converge and you start retrieving the probe as well, you actually converge to a higher PSNR in dBs as compared to without probe retrieval. And while ePy and pi, while they are all still converging, they are at least like 5 dBs less when we put the cutoff time, which is 200 seconds, because we want to look at the accuracies within a given time frame. So yeah, so we actually come up with an algorithm that works the step scan with probe retrieval and achieves a higher PSNR. So we had this plot where we positioned the different algorithms according to regions that they cover in the accuracy versus acquisition speed versus accuracy plot. But wouldn't this be the best place to be? Like an algorithm that's fast in acquisition, which is Fleischer, and also gets the accuracy of it's higher than multi-probe ePy. And we think so, but a naive way of implementing that would be, since we got accuracy just using the same error function, but with the TensorFlow, we can do the same cost function that we have for multi-probe ePy and implement it as an ADP algorithm, and we get good results. But I think we can do better. We can do better in the sense that multi-probe ePy does not model the physical forward model, and so we want to come up with a Fleischer ADP algorithm that actually reconstructs the object according to a real physical model. And if you remember, this was the Fleischer, this was the way the Fleischer worked. And if you look at one Fleiss patch and you have the probe, in physical model, what happens is this probe is moving and continuously integrating the diffraction, the magnitude of diffraction patterns, which we can model as the probe moving, but at discrete points, we generate these diffraction patterns and then take an incoherent sum of these diffraction patterns to give the predicted intensities. So mathematically, you would want to calculate a wave function psi of ij, where I is the ith like spot in the object, and j is the multiple of the discretization parameter that you use, and delta is the step size that you take to discretize this whole space. And once you have psi ij, you can just sum over the ith index, which will be like incoherent sum of the intensities, and you have a predicted intensity, a L2 norm over this over the magnitudes of the predicted intensities, and the real intensities would give you the error function. And then we go ahead and implement this as a computational graph, and let TensorFlow calculate the gradients for this error function and make the updates to the object and as well as the probe. And we see that we can achieve about like 8 dBs of performance over ePy in the time frame we are looking at. And in this case, ePy also seems to be converging. Also, this is reconstructing probe, of course, gives us better reconstruction results than if we did not reconstruct the probe as well as the object. And yes, and just to put ePy and ADP on the same level, we actually ran both of these algorithms in GPU-optimized library, TensorFlow in AD, and Tycolib in case of ePy. And so we went. So these results are on simulated data of the chips, chip images that we generated using a virtual testbed, and these are the visual results. So this is the ground truth object, and this is the reconstruction from multi-probe ePy. You can see that the edges are very blurred, whereas the Fleischer ADP reconstructions, the edges are very sharp, as well as you see these are like these are not noise. These are very tiny features that you also get to reconstruct in Fleischer, but not in multi-probe ePy. Just to quantify that, you see we plotted the absolute error with respect to the ground truth along the horizontal and vertical lines. And the red is that for multi-probe ePy, and you see that's higher, the absolute error is higher than that of Fleischer and ADP, both in vertical and horizontal directions. And just to validate that we have an algorithm that also works in real scenarios, we actually collected, or we used the data that was collected at Argonne National Lab on a Hynix DRAM chip using a fly scanning technique. And we use the data on our ADP, using our ADP algorithm, we reconstruct the chip, and we see that we can get resolution or like 90% to 10% edge strength accuracy up to 23 nanometers, which is within the definition of nanoscale that we define as 25 nanometers. So, yeah. And in conclusion, I would like to say that we extended step scan ADP to probe retrieval. Because we realize that probe retrieval is very necessary in real, in actual application of the algorithm. We also modeled Fleischer forward model and implemented a single probe Fleischer ADP algorithm that takes into account the forward model and reconstructs the probe as well as the object. Also, we show improvement over the state of the art in both STEP and Fleischer. As a future work, since we now have this framework, TensorFlow framework, which can calculate gradients through very, very complicated error functions. We want to model partial and spatial temporal incoherences into the forward model as well as we want to be able to come up with a way of selecting the step size and mini batch instead of hand tuning these hyperparameters for optimization. The other is you want to implement ADP as a distributed multi-GPU algorithm instead of running on a single GPU because that increases your efficiency, and explore the effect of regularizers as well, because in this case we do not have any prior information about what the chips look like, and we might be able to do better if we have some regularizers that take that prior into account. Thank you.
All right, any questions? So you mentioned the need to adjust the step size, but isn't Adam supposed to be very automatic in that regard, like very invariant to the original step size?
Yeah, it's supposed to be invariant to the step size, but you do have to give it a learning rate or a step size which then takes into account. So you have to give it a learning rate, and then it adjusts that learning rate based on how the things proceed in the optimization. And so we saw that having a very high or very low learning rate initially actually gives bad reconstruction. There is an optimal learning rate for that.
Okay. And can you try to use second-order optimization methods in this case? Like if you were able to compute second-order derivatives for this objective function you are using, would that help a lot, or is that even possible in this case?
So far, we haven't looked into the second-order optimization techniques, but I believe if we have a simple way of calculating second-order derivatives for complicated functions like the ones we saw, probably it could lead to faster convergence.
Anyone else from the audience? I had one more question. How close do you know you are to the global minimum in this case? So your local minimum, the local minimum you reach depends a lot on your initialization. So do you have a sense of how close to the global minimum you are in the problem you are solving with your initialization?
The spaces, there's no direct way of knowing how close we are to the global minimum. I think that's the case with most gradient descent algorithms, and that is why we use gradient descent algorithm. But the only measure you can have is how close the reconstructions are to your ground truth in simulations, or like how sharp the edges are in case of experimental data. And if you're the other question you ask is if the reconstructions are very close to your ground truth data, do you even care if it's the global minima or the local minima?
All right. Great. Let's thank our speaker again.
Okay. Thank you for the introduction. So hi everyone. Thank you for coming to my talk on Sunday morning. I'm Fengqiang. I'm from Northwestern. I'm also from Northwestern University. So today I'm going to give introduction of previous work achieving macro resolution time-of-flight imaging with the Superheterodyne interferometry. So this is a joint work between Northwestern University, Southern Methodist University, and the University of Wisconsin-Madison. So I will just go straight to the talk. So I think many of you here are familiar with this continuous wave time-of-flight imaging. We can also refer as the time-of-flight cameras. So in the time-of-flight cameras, basically we know we have a controller which is going to send out 2 radio frequencies. And one radio frequency with MT is going to control the amplitude of the light source. And the second radio frequency, RT, is going to send to the camera as the reference signal. And basically what the camera does is the beam coming from the laser diode is going to illuminate the object, and the camera will detect the reflection signal from bouncing back from the object, and the camera then will output the autocorrelation between the reflection signal and the reference signal, and then integral over some time. So intuitively, we can think about it as this way. So here is our signal coming from the object, and this is our reference signal. So basically, the sensor is doing is comparing the phase delay between these two signals, because the phase here, the phase P, is going to encode the depth information. So let me give you more like a math here. So basically, how can we use this autocorrelation signal to estimate the depth information? So basically, we will first introduce another like a phase constant phase delay in the reference signal here, and then we can change this phase so usually we'll change it 4 times, which is also known as the 4-bucket method, and then we can estimate the phase value here. And then after once we estimate the phase, we can use this formula here to estimate the depth information. So in this formula, C is the speed of light, and FT is the modulation frequency. So which is usually tens of megahertz, for example, 80 megahertz. And the phase P is the phase we just estimated. So based on this principle, there are many commercial products. For example, the PMD sensor and the Microsoft Kinect sensor, I guess many of you are familiar with, and also the time-of-flight sensor from Texas Instruments. So with this type of sensor, there are a lot of applications. For example, it can be used in the autonomous cars, and it can also be used in the robotics. It can also be used in VR or AR systems. So I think many of you are probably familiar with this human-computer interaction. For example, when you play games with the Xbox games. So let's say if we have an object here, which is a statue, and its size is about like 20 centimeter by 40 centimeter. Let's say if we use a state-of-art time-of-flight cameras to take an image. So here's probably what you will get. So even though you have the 3D information, but you basically lose it's very hard to visualize the contour of the face, such as the small details on the eyes and also the nose, because nose area has very small depth variance. So the reason is because the depth resolution for current ToF cameras is only centimeters. So it is really hard for us to visualize those small details. So what do we want to do in this project? So what we want is quite simple. We want to propose some continuous wave time-of-flight imager which can have some millimeter resolution. So with this resolution, we want to visualize those very fine details, such as you can see the eyes, the eyeballs on the eyes, and also the nose. So before I introduce our technique, I would like to remind you about how we estimate the depth information in the time-of-flight cameras. So if you can recall, this is our depth estimation, right? So as you can see here, the depth resolution is going to be proportional to the modulation frequency. So the higher modulation frequency, the better depth resolution we'll have. At the same time, of course, we'll have shorter image range. So the straight way is, okay, can we just increase the modulation frequency from currently 80 megahertz or 100 megahertz to 1 gigahertz or even terahertz? So the answer is for current the short answer for ToF camera is no, because the current time-of-flight camera, the imager is still silicon-based chips. So it's very hard for the silicon chips to respond to gigahertz or even terahertz modulation. So in this project, we basically propose like a novel way using interferometry to generate this gigahertz and terahertz modulation frequency. So our basic idea is still we are going to increase the modulation frequency, but we just use the interferometry to generate this gigahertz or terahertz frequency. So before talking about our technique, I would like to briefly remind you there's basically another type of continuous wave time-of-flight imaging. So as many of you may know, light is also a type of wave. It's an electromagnetic wave. So if we simplify this wave, you can say the frequency for this wave is going to be optical frequency. So let me give you one example how large is this frequency. So for example, if we have a 1,550 nanometer laser beam, and the frequency is going to be almost 200 terahertz. As you can see, if we can use this high frequency, we will achieve extremely high depth resolution. So of course, these many people have done that. So for example, in the microsync interferometry, what it does is we'll use a laser beam with the optical frequency of mu, and then we will split the beam in two arms. So one is going to the reference beam and then bouncing back to the detector, and the other portion of the beam is going to illuminate the object and then bouncing back to the detector. I think on Friday, Tommy Hero from MIT, he has given a very detail of the how the interferometry works, even though his type is Alexander interferometry, but it's very similar with the maximum interferometry. So, how can we get the depth information with the maximum interferometry? So intuitively, you can think in this way. So here's our signal from the sample, and this is the signal coming from the reference mirror. And we also compare the phase delay between these two signals. And the phase delay here is going to encode the depth information. So let me briefly walk you through the maximum interferometry. So in the maximum interferometry, usually we will have a beam splitter. So the light source coming from laser going to split in two arms. So one arm we call the reference arm. So the beam is going to the mirror and then coming back to the detector. So if we write out the electric field, we'll say this is the alpha is going to be our intensity reduction, and this part is going to be the phase introduced by the optical path from the beam splitter to the mirror, which is L1. And the second portion of the beam is going to illuminate the object. And similarly, we can write out the electric field here, and there's also another phase introduced by the optical path from the beam splitter to the object. So the distance is L2. Of course, these two beams will arrive at the detector simultaneously. So we will basically sum these two signals from the reference arm and from the sample arm, which is also we call the interference signal. So we can further write out this intensity in this way. So it's a cosine term. And then this term is here is going to encode the phase information. So the L1 and L2 minus L2, we also call it like optical path difference. And in this optical path difference, it will encode the depth information. So once we estimate the phase here, we can use this formula here to estimate the depth information. As you can see here, this depth estimation is exactly the same with the regular time-of-flight camera. The difference is just the modulation frequency here is different. So the modulation frequency is optical frequency, which is hundreds of terahertz, much higher. So let's say if we put these two types of continuous wave time-of-flight imaging together, and in the same plot. So the x-axis is going to be our image range, the ambiguity image range, and the y-axis is going to be our depth resolution. As you can see, with time-of-flight cameras, we use tens of megahertz modulation frequency. So the benefit with these modulation frequencies will achieve extremely high image range. But at the same time, our depth resolution is going to be very limited to centimeters. So on the other hand, we have the maximum interferometry at the bottom. So because the modulation frequency is extremely high, then we will achieve very high depth resolution. But on the other hand, we will have very very limited image range. So of course, many people say, okay, I can just do phase wrapping with different multi-frequencies. But in this project, we are interested in to image some object with rough surface. For example, the walls or the statue. So fundamentally, maximum interferometry cannot image this object with rough surface due to the speckle issue. So when we plot these two types of imaging techniques as you hear, you can see there's something like missing between. So basically, this is what we want to do. Okay, can we propose something time-of-flight imager with the modulation frequency between these two things? Or our initial idea is, okay, can we combine these two different techniques? Can we use the interferometry to basically to generate the gigahertz or terahertz frequency? So let me briefly talk about how we do it. So basically, we're still using the interferometry setup. So as you can see here, we will use two lasers simultaneously in the system. So the two lasers will have very close wavelengths or close modulation or close optical frequencies. So basically, intuitively, you can think in this way. So we have two laser beams coming from the source, and then they will interfere with each other. And in the interference signal, you will have two components. One component is this high frequency component, the high frequency components, and the second component is this low frequency envelope, which is the optical beam low frequency. And what we want to do is we can use our SH-ToF imager basically to select out this low frequency envelope, which we also call the optical beam low frequency, which is going to be the mu2 minus mu1. And the mu1 is the frequency for laser 1, and the mu2 is the frequency for laser 2. So as you can see, now we basically generate this gigahertz or terahertz modulation frequency. And we are going to use this frequency as our modulation frequency in the time of flight setup. So if we compare these three different types of imaging, as you can see clearly, the depth estimation method is exactly the same. The only difference is, again, the modulation frequency. So in microscope interferometry, we got like hundreds of terahertz modulation frequency. And in time of flight camera, we got tens of megahertz modulation frequency. And what we propose is between from 1 gigahertz to 1 terahertz. So let me briefly summarize our contribution in this project. So basically, we propose this SH-ToF framework, and in our framework, we have the tunability of the image range and the depth resolution. And we also build a prototype which can help us do the 3D scanning on the optical rough surface. So let me give you more details how we build. How does this SH-ToF works? So as I mentioned earlier, there are two lasers in the system. But to simplify, let me introduce one by one. So if we turn on one laser, so the beam is going to speed by this beam splitter, and the portion of the beam is going to the reference mirror. So we put a component called acousto optical modulator, or AOM, on the reference arm. And what does this AOM work? It will upshift the optical frequency by FM1. This FM1 is introduced by the AOM. So as you can see here now, in the reference arm, the frequency is going to be mu1 plus FM1, and the mu1 is the optical frequency. And on the sample arm, so the beam is going to illuminate the object, and as you can see here, the frequency is still optical frequency mu1. So at the detector, of course, we will get this interference signal, and in the signal, as you can see here, this is the phase introduced by the optical path, and the L is the optical path difference between the sample arm and the reference arm, and that component is going to encode the depth information, and that is what we are interested in. And the FM1 is the frequency introduced by the AOM. So similarly, for the second laser, we also put another AOM on the reference arm, and it will also upshift the frequency by FM2. And similarly, we will also have this phase information, and also with the AOM frequency FM2. So of course, this two laser beam is going to arrive at the detector simultaneously. So as you can see here, we will have the interference signal for laser 1 and laser 2. So what we do is we do quadratic censoring after we achieve the interference signal. So we just square the signal. You can think as we square the signal. So after we square the signal, of course, we will have many components with different frequencies. For example, FM1 plus FM2 and FM1 minus FM2 and 2 times FM1, of course. So, but we are interested in this term, FM1 minus FM2. We are interested in this component. The reason is because it will encode the optical modulation frequency. And after we select, and basically what we do, we use a bandpass filter to select out this frequency, and then we do the Fourier transform to estimate this phase. So as you can see here, this is going to be modulated by the optical beat frequency. And once we estimate, we can use this formula to estimate the distance here. So here is the optical modulation frequency. And I have introduced this principle. So now, based on this principle, we have built this prototype. So in this prototype, we see this is our two lasers. As you can see here, it's extremely small. And of course, at the same time, it's like cheap compared to other lasers. And also, our setup is a fiber-based setup. So we put all the components in just on this small piece of breadboard. And for the detection, since we're doing the single pixel detection, so we're using this galvo to scan the beam on the object, and then so that's how we get the 3D profile. And the laser, the center wavelength for the laser is 1,550 nanometer, and the AR modulation frequency is 40 and 40.1 megahertz. And the laser we have is tunable, so that's why we got this tunable modulation frequency. So after we build the prototype, the first thing we want to do, of course, is we want to verify our prototype. How good is our prototype? So first we verify is, okay, what is the upper bound performance of our setup? What we do is we basically fix the beam. We focus the beam on the cardboard and fix the beam and then do tensile measurement. We then basically add, so we try different modulation frequencies from 100 gigahertz to 6.25 gigahertz. So the corresponding wavelength is going to be 3 millimeter and 48 millimeter. So as you can see here, with the higher modulation frequency, we got a extremely high depth precision. And when we reduce the modulation frequency, we will have a worse depth precision, but it's still in sub-millimeter. And we also estimate the phase precision. As you can see here, the phase precision is relatively the same for different modulation frequencies. We also built a simulator based on our physical setup, and we test our simulator with different signal-to-noise ratio. As you know, like signal-to-noise ratio is going to affect our precision. So, but roughly, as you can see, interesting is like the phase precision is going to be the same for different modulation frequencies, and we also roughly estimate our prototype the signal-to-noise ratio, and it aligns very well with the simulator. Of course, we can at the same time we can use this the depth estimation to quantify the depth precision as well. And we also compare our experiment results with the simulation results, and it also aligns very well. So as I mentioned earlier, we're not going to image only single point. We're going to scan the beams. So the next thing is can we verify the performance when we're scanning the beams? So what we do is we do the line scanning setup. So we will scan the beams along this cardboard, and if we use the center beam as a reference, as you can see here, the depth profile is going to be a quadratic, and it will be symmetric when we scan the beams at different angles. So we also try different modulation frequencies from 100 gigahertz to 6.25 gigahertz. I would like to take your attention here, as you can see, with higher modulation frequency, the depth precision is much better compared to the scanning profile here. But the problem is with higher modulation frequency, the image range is going to be limited. So that's why you see here we have the phase wrapping problem. But of course, we can just do the phase wrapping and then reconstruct the profile, and then we estimate the precision, and then we basically fit the ground truth of this profile, because we can calibrate the distance from the beam to the sensor, and then we quantify the depth precision. As you can see here, with higher modulation frequency, we got a better depth precision. But all this precision, as you can see, with different modulation frequency, is in sub-millimeter. So once we verify the point scanning and line scanning setup, then of course we can use the prototype to do a 3D scanning on the rough surface. So again, this is the object we tested. The surface is rough, and the size is about 20 centimeter by 40 centimeter. And this is the rendering results based on our SH-ToF scanning. And the modulation frequency we use for this result is 6.25 gigahertz, and the corresponding wavelength is 48 millimeter. And if we compare our scanning results with the regular time-of-flight results, as you can see here, we clearly visualize those very fine details, such as the eyeball in the eyes, but we totally miss them in the regular time-of-flight scanning. So we can also take a look at from the side view. As you can see here, we can see different layers with our scanning, but you totally miss that in the regular time-of-flight cameras. So of course, as you know, we are doing the point scanning, which is very time consuming. So we are thinking, okay, can we do like a focal plane SH-ToF? And yes, so we are currently building this setup, and since the modulation frequency is very high, and as many you may know, like people are using the time of flight to do the looking around corner. And we are also part of the data review project, and we are also thinking about using this technique to do the looking around corner problems. So to summarize, we propose a SH-ToF framework, which is very compact, and we also built a prototype to demo the macro depth resolution. And the one advantage of our system is we are using this tunable source, so which can give us the flexibility between the image range and the resolution. So if you are interested in our work, you can take a look at our previous publication in Applied Optics and our ICCP paper. Thank you.
Thanks, Fengqiang. We have time for one question. Anybody from the audience?
Thank you. So yeah, that's a very good question. So basically, we are doing line scanning. So you see so basically that's the registration problem, because one time we only do one line scanning, and then we do the second line scanning. So this is the error between these two line scanning, and yeah, due to some registration problem and some hardware problem. If you are interested, I can tell you more about these details. Yeah.
All right, let's take Fengqiang again.
Okay. I'm going to talk about how to improve spatial resolution in long-distance imaging. And before we do that, I want to sort of define what long distance means, because it depends on the context. Right? It could mean that I want to image somebody who's a kilometer away and be able to make out their face and run some recognition algorithm. Or it could be that I'm interested in something smaller, like a fingerprint at a shorter distance. So maybe 1 to 50 meters. Right? But we all know that there are limitations in our existing camera systems that prevent us from being able to infinitely resolve features, despite what the media would like us to believe. So if I just try to zoom in on this person walking down the street, taking with a cell phone camera, I can't see them, right? We cannot recognize them, even though they're not really that far away. And there are many reasons why our spatial resolution is limited in imaging, right? We have all sorts of lens optimization problems, defocus blur, the object could be moving, or there could be noise due to low light level. Now, fortunately, as we've seen over the past few years and decades, we have many techniques to solve those. However, there's still one fundamental limit that we cannot so easily address in post-processing, and that is diffraction blur. Now, diffraction is represented by an airy disk for a circular aperture, and the radius of the spot size on the sensor is related to the wavelength of the light, the focal length of the lens, and the diameter of the aperture. And from this equation, we can see that if I want to reduce the diffraction spot size,
which would improve my resolution, I need to either change the light that I'm using, not so nice if we want to take a color photo, decrease the focal length, or increase the lens aperture. And now the reason that this is important is that the diffraction spot size on my sensor, due to the magnification of the lens, gets blown up on the object side so that what may seem like a very small 1, 2, 3 micron, or, micron spot size actually fills up a meter or more. So all that information gets averaged together. And we need to reduce this. But we look at our existing cameras, such as the common smartphone camera that everyone uses. Here we'll plot resolution versus distance. And we see that the ability to resolve for a smartphone camera, something like a face, is limited to maybe at most 4 to 5 to 10 meters. Right? So if I want to image that same face a kilometer away, I can't use a smartphone. Right? As I mentioned, one way to get around this problem is to zoom in, yes, but that increases diffraction, so we also increase our aperture diameter. And if we look at other common cameras, like a point and shoot, okay, well now I'm out a little bit further. But if I really want to push towards this 1 kilometer distance, I would need something that's a little more exotic, right? So something with a very large focal length and a very large diameter. Now, they exist, these sorts of lenses exist, but there's a huge trade-off. And that is, as I sort of increase my lens size, the weight also increases significantly, as does the cost. Right? And so the goal of this talk will be to show you that we have a technique that hopefully can work somewhere in this regime using cheaper lenses, which also means smaller lenses, yet still achieve a similar performance that we might have with something that's larger and more expensive. Now, in order to do this, I'm going to borrow an idea from the radar community, which is that they have the same problem. They have an emitter, a coherent source, and they have a limited aperture, and so that when they try to image the ground, it comes back and it's diffraction limited. And so what they do is they create a synthetic aperture. They take a measurement, and then they move their detector, take another measurement, move, take another measurement, and at the end, they combine these individual measurements to reconstruct a high-resolution image. Now, we're going to do basically the same thing for visible imaging. I'm going to take a camera and a coherent source, illuminate my scene, and then move my camera up and down to get individual measurements. These are intensity measurements without phase, and that'll become important in a second. Recover the phase computationally to get a high-resolution image. Now, the forward model for this process is fairly simple. I have a illumination source. A coherent illumination source hits an object, reflects back towards my camera over a sufficient distance to undergo a Fourier transform, a scaled Fourier transform. It intersects my camera lens, which acts as a bandpass filter, only allowing a portion of the Fourier domain to pass through. And then inside of the camera, we undergo another Fourier transform, which satisfies Fraunhofer diffraction, onto the sensor. Okay? So we have linear Fourier transform, linear bandpass filter, linear Fourier transform onto the sensor. However, once our incident plane hits the sensor, we have a nonlinear operation. So the lens forms the Fourier transform, but the sensor cannot capture the full field. This is operating at terahertz. Our electronics are insufficiently fast to capture it. And so we only end up with an intensity measurement, which is the square of the field's magnitude. Now, to illustrate what this looks like, let's see. So to illustrate what that looks like, if I take this synthetic or simulation data, I have my true object, its Fourier transform, which is bandpass filtered by this red circle, and then the image that you would observe on a sensor. And as I move the camera around, the aperture around, we capture different bandpass regions of the Fourier transform and get different frequencies. And so the idea is that if we can capture sufficiently large region of the Fourier transform and take multiple such measurements, we can then stitch them together and have a synthetic aperture, which would give me a greater number of higher frequencies and more spatial resolution. Now, there's a small hiccup here, and that is you can't simply stitch things together in frequency space, in the Fourier domain, if you do not have both the magnitude and the phase information. And we only have the magnitude, or the square of the magnitude. And so we need to recover this phase information through a process cleverly called phase retrieval. And this is formulated as a fairly straightforward optimization function, just least squares over all of my different measurements. But because I'm trying to enforce a constraint on the magnitudes that I've observed, which is a nonlinear process, I end up with this nonlinear non-convex optimization. And so we're going to use an iterative procedure to recover phase in one domain, spatial domain, go back into the Fourier domain, and repeat until we converge. And this is, all these iterative solvers are based on a Gershberg-Saxon type solver, and the algorithm that we use, it follows from the work of Wu et al. And Tien et al. And sort of simply put, I take my complex field, which is, sorry, it's cut off here. Take complex field in the aperture domain, right? So the field that intersects my lens. Take some region that passes through. Take the Fourier transform onto the sensor, right? And so now there's some arbitrary phase, which is incorrect, and some arbitrary magnitude, which may also be incorrect. Enforce the correct magnitude that I've observed, leaving the phase untouched. Bring it back into the aperture plane through the inverse Fourier transform, where we now have updated estimates of that complex wavefront, and then move to the next region and repeat, rinse and repeat. And then we'll go through the entire Fourier region, have some global estimate, which is still incorrect, and then do it again, right? And we'll keep doing these sort of iterations until we're satisfied that the optimization has converged. Now, Fourier Ptychography has been in use for 5 to 6 years now, and we know that it works very well. So here we have some observed low-resolution images. These are all tabletop implementations done on an optical table, so they're not at kilometer distance, no worries. We're not shining lasers across the lanes of traffic. So we have observed images with F number of 32 that are blurry and difficult to see, and then using Fourier Ptychography, we were able to recover 4 to 6x improvement in this experiment. Okay. Now, like I said, the field's fairly established, and it is known that this works for objects that are heavily forwardly scattering or optically smooth, right? So in areas like microscopy where you're shining through a cell, this works very well. However, most everyday objects are not smooth, at least not optically smooth, and you have surface variations that cause a dephasing of the coherent light. We're using a laser source, causes dephasing, and we end up with speckle, right? So the observation that we would make, so if we run the same experiment but allow it to have some random phase, we see that our observed image is not quite the same. And in fact, if we were to move into different regions of the Fourier domain, all of our observations are seemingly identical to the eye, right? They're similar. Now, in this case, I'm interested in capturing the intensity image, high resolution intensity image, and this speckle appears to be an awful lot like noise. Now, it's not noise in the classical sense, right? This is a physical phenomena, and it's not random, right? And it can give me material properties, but it sure looks like noise if all I want is a high resolution image. And so in order to account for it, in our iterative phase retrieval, we just add a denoising loop. So each time, we sort of go through the individual apertures, and as we scan through, we just run a denoising loop where we take the whole synthetic aperture, go into the spatial domain, denoise an estimate of the amplitude, and then come back as we repeat. And this has a nice property of not improving spatial resolution, right? We haven't actually added more information, but it suppresses some of the variation due to the speckle, and it improves the apparent contrast. Now, the physical setup that I'm going to use to capture these sort of everyday objects is that I'm going to have a coherent source that gets blown up, focuses on an object, and then we capture through scanning. The prototype is implemented on an optical table where we have our laser and lens path hits an object and comes back to a camera that is on a 2D translation stage so that I can move and capture different regions of the Fourier space. And then the object that we're looking at is going to be 1 meter away, so 2 meters round trip. And then the camera in this experiment is going to be scanned on a regular grid. This is not a requirement. We can sort of use any pattern that we wish, provided that there's sufficient overlap. Though was not mentioned, it is important to note that our measurements that we capture are overlapping. Because we are missing the phase information, we're going to use redundant measurements in our recovery process. So we're going to scan our camera around to create an aperture that is 6 times larger than the original lens's aperture. Right, and I can show you some of the results of doing this process, right? Where if we have a diffuse fingerprint, which is just a fingerprint that has been perhaps dusted with a powder or left in a substance that may have been contaminated, you end up with an image that exhibits speckle, and we cannot make out any features. And after running using our technique, we're able to recover the fine ridge detail of the fingerprint. Similarly, for the reverse side of a $2 bill, with a regular camera, we cannot make out any of the details, and then using Savvy, we're able to recover the scene. Now, we can characterize the performance of our technique using an Air Force target, a resolution target. So here we have the image that it would be captured with just the one observation. And as we zoom in, there's no discernible data, right? You cannot make out any of the features. Now, you could say, well, I've taken a optics class, or I've dealt with speckle before, and I know that if I just average a couple of frames together, or if I try to destroy some of the temporal coherence by vibrating the source, I can remove some of the speckle, and that's true. So we do this. We average images together or vibrate either the source or the target. The speckle reduces, but it does not vanish, and so we still are unable to resolve many of the fine features. But if we use our Savvy technique, we're able to not only see the general structure, but even further down, right? We are able to image features that are 6 times smaller than our original capture. And so just sort of to illustrate on a larger scale, this is the original, or this is one observation, and then after we use Savvy. Right? And then we can characterize this by looking at the expected resolution. So the resolution target, if you're unfamiliar, uses bars with a known line pair spacing. And so if we look on the right horizontal axis, this is going to be a resolution in line pairs per millimeter. And I would expect, sorry for the confusion here, the solid line is the theory, right? It says that as we increase our aperture by a factor of 2, our resolution should go by a factor of 2, and so on. And as we do increase our aperture diameter, we notice that we follow this line fairly closely. And then another way that we can confirm that we are that our resolution gains are realized is that if we look at the size of the speckle is also related to the amount of diffraction. So as we increase the aperture, the size of the speckle should decrease, and is inversely proportional, and we find that we track that very well. So I want to leave you with the following, that the analysis represented here addresses one particular problem, right? And that is, can we record high-resolution images with significantly cheaper optics? And the answer is yes, if we are willing to allow for a little bit of flexibility in our image capture system, right? Now, what I've shown is for a translating stage, but there's no fundamental reason that we cannot make an array of images and then either move our laser source to introduce diversity or move the array itself a few times. And then we've also demonstrated that Fourier ptychography and the use of SAVI is a viable system for achieving this goal. I'd like to thank the co-authors on my papers, right? Ashok Viragavan, Ali Cossairt, Yicheng Wu, Minosh Sharma, Salman Asif, Roar Korsmeyer, and Nathan Mitsuda. And if you'd like to find any more information on this work, you're welcome to, I invite you to look at either my webpage or the lab webpage at Northwestern. All right, thank you.
Thanks, Jason. We have time for questions. Anybody from the audience? Go ahead.
Mm-hmm. Oh, yes, I see. So the question is that the images seem to be binary with a fairly high contrast. Does this work? Does this technique work for something that it has gradations? So there was one result with the $2 bill that does have some gradation, and the technique does work. We do have a result in the paper, though it's not shown here, that addresses this. So the challenge is that as you introduce gray levels, the contrast that you get with the laser and the speckle is affected, right? It decreases. And so we find that you just require slightly more overlap in the data acquisition in order, a little more redundancy to make it work reasonably well. But it can work. So there's no limitation in that regard. Actually, Laura Waller's group has shown for a microscope the inverse, that if I have multiple light sources in a single camera, can I basically do the same? And they have results at least at 15 frames per second that I know of. And you could do the inverse if you had multiple cameras. However, there's one caveat, that you have to have overlapping measurements. So you could have multiple cameras, but you would also potentially need multiple light sources in order to have the sufficient data redundancy to recover the phase. Mm-hmm. Mm-hmm. So part of the process that can be done with ptychography, and it is done here, is to recover the pupil function for the lens. And so you could either, I mean, I'll cheat and say you can just calibrate the system, right? If I knew the lens behavior a priori, okay, you're fine. Or if you just have perhaps sufficient overlap even within a lens, just do a estimate of the aberration of each individual lens, I think that you can adjust for this after the fact. I don't see that as necessarily being the main limitation. I think Ashwin had one last question. Yeah. Without denoising? No. Though I didn't show it, they look similar. The denoising just suppresses some of the contrast that's introduced by the speckle, so that the apparent quality increases, right? So basically, what the phase is doing is it's redistributing the intensity in a local neighborhood, and so we're just smoothing that out a little, but the resolution itself hasn't changed.
All right, let's thank Jason again.
Hey, good morning, everyone. I'd like to thank the organizers for inviting me and for you folks for joining me in this marathon session. I've really enjoyed this conference, and I want to talk today about some work in coherence engineering and light field imaging we've been doing at Princeton. And there's many variables to the planoptic function. And the ones I want to focus on now are just the spatial properties. Okay, we normally think of intensity and phase, but I want to talk about statistical light, where at every point in X, there's going to be some distribution of rays, okay, which I'm going to term an angular spectrum. Okay, so in this case, you might have sunlight or the lights overhead, which may start off as uniform intensity, or roughly so. They have some distribution that then changes when that illumination hits an object. Okay, in these cases, it's obvious that the intensity changes, but very often you can't see this, and the statistics of the object, the texture here, will show up in the statistics of the light. And there are many example problems that we're trying to deal with, some of which have been mentioned at this conference, trying to see through clouds, for example, or look at the surface of skin, or try and get your reflection from a wall, right? Where you know that there are some rays that are bouncing straight back at you, but you normally can't see that signal because it's lost in all that scattered noise. Okay? So the talk is split up into two different parts. The first, I'm going to talk a little bit about measuring the spatial coherence. So that's essentially light field imaging. Okay, so we can get a feel for how scattered light behaves. And then once we have adequate measurements, I'm going to talk about engineering the coherence, right? So that we can see how well we're doing once we structure that light. Okay, it's very much like structured illumination for intensity, or changing the phase, kind of like computer-generated holography. We're just going to go to the next step and structure the spatial statistics and see if that's useful. So here's a typical light field image. We're familiar with just an array of lenses over here. And what you're doing is you're sampling the wavefront with each of these lenses, then doing basically a local Fourier transform to get the angular spread. And you'd like the measurements here to be separated so those angular spreads don't overlap, right? You can discriminate the information. Okay? And this limits the resolution of your light field camera. Because essentially what you're doing is you're taking some pixel array, and instead of mapping all your points on your object to points, so you get just information in X, you're using some of those pixels to get angular information as well, right? So it's a compromise. And there have been many techniques to try and overcome this limit in resolution. For example, trying to expand the bandwidth over here, right, or super resolution techniques. From the other side, if you just take the photograph itself, maybe you want to add depth to it, right? Get phase or envelope phase information, which is essentially trying to recover the Fourier spectrum or something like this. Okay. What I'm going to do is just the other end of computational imaging, right? Where if you have the limit of one picture, let's simply take two pictures, right, and add them together. Combine them in some fashion. Right? So on the left, we have kind of X and K information, but on a coarse grid. On the right, we have very fine resolution in X, but no K information. But we know that the Fourier spectrum, or the angular spectrum, is related to position. Okay? And we're going to use our light field measurement as a constraint to fill in those gaps. So it's very much like a phase retrieval algorithm, where you go back and forth. The nice part is it's just Fourier relations, so this can be very fast, and it converges relatively quickly, okay, a few iterations. Experimentally, it's not so bad. As long as you have enough light, you take a beam splitter, send part of your light into a regular camera, part of it into a light field camera, and then do the algorithm on top of this. So here's an example of how this works. The top view is a normal light field camera, just a lens lit array, on a resolution chart, and this chart is tilted, so we get some depth to it. And you can see that the resolution on top isn't terribly good. Okay. When you use a normal camera, of course, you can get high resolution in X, but you also get this extra depth information from the light field part that allows you to digitally refocus at other points along the chart. Okay. For a more realistic example, let's take a human cheek cell. Okay. It's mostly water, so there's not much intensity absorption. This is really a phase object. So if I put this cell in the focal plane, I don't really see any intensity variations. There's a little bit around the edge, but not much on the inside. Okay. So here's the picture I'm taking at the focal plane. And then once I have the angular information, I can numerically refocus before and after that focal plane. Okay. So you see the nucleus is thicker than the rest of the cell. Okay, it basically looks like an egg or something like that. So as you move away from the focal plane, you can see focusing effects, okay, and with the other organelles as well. Okay. Because you're basing it on a normal picture, the resolution is as good as you can get with your microscope. Okay, in this case, we really are diffraction limited to about half a micron, okay, which means in order to get the phase, we can use a transport of intensity equation, equating the diffraction to changes in our intensity. And because all of this is calibrated, we can do everything quantitatively. Right? So we can get a height map, for example, of the cell itself. For the experiments that are coming up, I'm going to be doing a different measurement of the light field, and not relying on numerics, but taking a pinhole aperture to localize my position in space, and then taking a lens to capture as many of those rays as possible. Okay? And then I'm just going to scan the aperture all the way along. Okay? So this is a slower process, but it directly evaluates the light field across the entire wavefront. And the aspect I want to focus on now is propagation, okay? Where I have position and momentum, so direction of the ray. So this goes by a lot of different names in a lot of different communities, and I'm going to refer to this as phase space, but it's really the basic form of the light field. And I'm showing a few example points here. They're color-coded, okay? So the red one and the blue one, for example, are at different positions, but they have the same angle. So same y-axis over here. Red and green, same position, but different angles. Okay, so they're separated vertically. And when you look at propagation, at least in geometrical optics, the rays just travel in straight lines. So at a farther distance, the angles are going to stay the same, the y-axis, but the positions change. So propagation amounts to a shear in phase space. Here's a numerical example of this. Here's the bars of the resolution chart again. And if you defocus or you diffract, you're going to get a blurred output if you just measure the intensity. But if you have one of these light field cameras, right, you get not only spatial information, but the direction of that ray, the angular information. This is really a 4D problem now, x and y, and then the angles, kx and ky. So it's easier to just take a slice of this, x on horizontal, angle vertical. And you can see once you have a light field image, you know what your object is. That's the 3 bars again. And they are in fact tilted because of propagation. And the amount of tilt tells you how far away from focus you are. Right? It's a very convenient measurement. So here's the setup. I'm going to use it as an aperture, not a pinhole that I mechanically scan, but a spatial light modulator, okay? Which is maybe a silly use of an expensive piece of equipment, but I'm going to throw out most of my light, let some of it transmit, scan that along, and the light that gets through gets imaged into an X-space camera, and then I do an optical Fourier transform to get the angular momentum. Okay, so easily controllable, no mechanical vibrations, right? I inherit all the goodness of an SLM. And here's an example experiment. I take my resolution chart, and I'm going to illuminate it now with 2 different types of light. The first is laser light, so it's coherent. Okay, you can see some interference effects. And then I'm going to send that laser light through a ground glass diffuser. So I rotate it. I change at time average the speckle over here. And you can see that that ground glass diffuser spreads out my rays. So I certainly get a bigger angular spectrum here in the vertical direction. In the coherent case, I have basically 3 slits. And that means individual single slit diffraction. So at the edges, I should expect to see some angular spread, which I do in this kind of dog bone structure. When you're partially coherent, you wash out that interference, and I don't get those fringes anymore. And now as I mechanically change my lens, so before and after focus, sure enough, you get the expected shear in phase space, right? With the degree of shear corresponding to the distance from focus. Going to a slightly more complex example, if I try and take some objects and send it through a thin diffuser, so I'm scattering the light over here, the objects are going to change the spatial statistics a little bit, perhaps not obvious from the intensity, but when you do a little math analysis on it, you can realize that the light field still carries its information through. So I can measure depth of these individual objects over here. Now what I'm going to do is slightly change the system, and instead of a spot that scans, I'm going to extend this into a line. Okay, so basically parallelize the process along one dimension here, and then take a lens, cylindrical lens, to capture the rays that come down. And I want to do this because I have a particular geometry I want to consider. I want to consider a microfluidic channel. So a channel of water over here, and I'm going to have a slit in the bottom of it to send in light. And you can see there's a certain angular spread that is then captured by my lens. Okay. And I want to do this because I want to start imaging biological samples that like to live in water. Okay. And instead of placing them individually on a slide, one after the other, I would just like to flow them through so I get high sample throughput. Okay. So instead of scanning this line all the way down my channel, I'm going to keep that line fixed and let the object do the scanning as it flows across. And since it's a slit, it's very easy to keep track of the object motion. Okay. And this particular experiment was designed to measure C. elegans. Okay. Very famous worms. In this case, they're glowing. Okay. I don't want to do the fluorescence. Okay. Maybe it's cytotoxic. Maybe I want to use fluorescence for other things. Right. I want it marker free. And I'd like to capture these guys as they're freely swimming, okay, which typically is not done in the community. Okay. In order to take a picture, you tend to fix these guys. Okay, mechanically pin them down, maybe anesthetize them, cool them off, or something like this. Okay, it's generally accepted that it's not harmful for the worm, okay, but I don't think they're too happy about it. Right? It also limits the throughput. Okay, this worm was the first multicellular organism to be genetically sequenced, so it's in a sense the workhorse of genetic biology. Okay, and you'd like to know a lot about it, so you know all the genes, but you don't know how they work. And you don't necessarily know how they react, right, to the environment, to drugs, to things like this. Okay? So it's very important to study the morphology of this under a variety of different circumstances. Okay? And what I'm going to do is I'm simply going to take this worm, put a little fluid pressure so that I encourage it to swim through the channel, and take a picture. Okay? So you can see it's going through. You can very clearly figure out the edges of the worm, so you don't have to worry about alignment and stitching pictures together or anything like this. Okay. This picture isn't all that intuitive, so instead I'm going to take different slices, so this particular plane and other cross sections, okay. And as this worm goes through, you basically get a slit that's scanning along, and you see here things that look very much like sinograms, okay, because that's exactly what they are. They're the basic projections you get from tomography because I'm doing different angles giving me different perspectives. It's not a full 360 degrees, it's limited angle tomography, but it still lets me get some 3D information. Right? I can piece together cross sections of the worms now with no markers, no pinning down, right? It's a very simple system to get some complex information. As an example, I can take optical slices now, just numerically, and here's the reproductive system, so you can see a series of eggs and so forth. If I change the height through the worm, I can look at the entire digestive tract from head to tail. Okay. If I had a normal two-dimensional picture, of course, all of these organs and systems are superimposed on one another, and it's very hard to discriminate things within the worm itself. So once you think about this, right, you introduce a fluid channel, you have motion, right? You can just leverage the motion in this new context. For example, if I tilt the channel, now as the object goes through, it goes through the focal plane, and if I take a series of frames, I get optical sections at different heights. If I know the point spread function, it's a simple matter of deconvolution to get 3D surface profiles. One of my more favorite examples is structured illumination, right? Where you have some finite numerical aperture to your lens, so you, of course, only get a limited set of rays that enter your system. And if you put a grating here, you can shift your system so that wave numbers that weren't originally seen are now visible. Okay? There's a little bit of ambiguity left and right, so typically you have to do phase shifts on your grating. Here, we're going to let the motion do the phase shifts. So in this case, I have small objects that are not visible, say their separation, in a normal diffraction limited system. The structured illumination gives me super resolution, so now I can see this. So maybe not fine details, but this is important for counting, okay, in a variety of types of experiments. This is a 1D grating. Typically, if you want to do this in the plane, you have to go 0 to 360, so you have to shift the gratings around. Okay? Previously done mechanically. Now, of course, we do this with a spatial light modulator. Okay? And this is where I want to shift gears a little bit and repurpose the spatial light modulator, not for structuring the illumination, but for structuring the coherence. Okay? Perhaps the simplest example is I take my laser light, send it through this piece of ground glass again, okay, so it scatters, and it's going to scatter and give me essentially a Gaussian distribution. Okay? Most of the rays go straight, a few of them fall off, right, as you get farther and farther out. I'm going to do an optical Fourier transform, so the spectrum's on this modulator, and now I simply shift the spectrum. Okay? I take some wave numbers, say, from the middle, and shift them towards the tails, so my Gaussian can become an exponential, or a Lorentzian, or make rectangular distributions, really pretty much whatever you want. Right? You can't tell so much in the intensity, but it's very easy to distinguish in the spectrum. Okay? So this isn't a full coherence function here. So every point x has the same angular spectrum over here because I'm doing it in the Fourier domain. What I really want is, as a function of position, I get different spectra. So what I'm going to do is I'm going to modify this kind of rotating diffuser argument and do a series of time frames with the modulator itself. Okay? So I'll make some random pattern on the modulator. Okay? It's got some known statistics. And I can have a set of pixels over here have different statistics from, say, a region somewhere else. If I time average, right, I can get something that's more and more uniform. And then I just take an image again, both in real space and in Fourier space. Here's a nice basic example where, again, positions on the horizontal axis, angular spectrums on the vertical. And you can see at this particular position, I have a relatively wide spectrum. As I move over, the spectrum gets narrow, so that's more coherent. As more rays are going forward, it widens again, and more narrow. Okay? I basically have a breathing of the coherence function. Okay? If I were to look at just the intensity, over here, it's essentially uniform. That's by construction. And if I were to take just the Fourier transform, I lose all the spatial information, and this just appears as a Gaussian. Okay? I need the local Fourier transform, the local angular spectrum, to see this kind of structure. And now you're really off to the races. Once you have this, right, you can, it's really a 4D problem, so I have some speckle pattern in position that gives me some angular distribution over here that I can change sizes or reorient or so forth. Right? So I can do basically a kind of coherence encoding if you want. The previous case with long and short coherence lengths are basically 0 and 1. Okay? It's not encrypted. Okay, it's just hidden. Okay? And I can do all sorts of designer illumination, changing my coherence properties. And as an amusing side note, right, this works for any kind of coherence, okay, including quantum optics. Okay? So if I have a generation of photon pairs, what I really care about is how correlated they are, or in quantum language, how entangled. Right? I have a photon over here and another one over here, and their fluctuations are related to each other. Okay? And normally, those fluctuations are what you get out of your conversion process. Here, we can take our modulator and adjusted at will. Right? So in intensity, nothing really changes. But over here, how I measure coincidence in my detectors can be sculpted. Okay? Periodic patterns, topological patterns, and so forth. Okay? And now here's where you start leveraging actual quantum security. Okay? Or you're really doing information processing because I'm manipulating the wavefront. Okay? There's a host of reasons you want to do that, including to power and observe quantum devices, right? Because I can now place photons in individual positions with targeted coherence. And that's really the take-home message. Right? So once you can measure your light field with high resolution, so you can be sure of what the coherence is doing, you can then use modulators to engineer it, okay? And structure it just like you would normally with intensity illumination or phase patterns. And then do all sorts of information processing and hopefully carry over the benefits of structured illumination to structured coherence. So with that, let me thank my students, current and past, for doing this work, the funding people for supporting it, and you folks for hearing me out.
We have time for questions, Ollie.
Sure. So this is essentially what the system looks like, okay? Except instead of having a diffuser here, I have a nonlinear crystal that takes a high energy photon and splits it into two, okay? And there's a lot of problems now where you're doing, say, long distance communication, right? You're sending entangled photons through turbulent air, okay? And in normal optics, we would say, just do adaptive optics and correct for it, okay? Now we can do adaptive quantum optics.
Anybody else from the audience? You mentioned about different applications of this coherence engineering. Can you go a little bit more detail about the 3D display example you mentioned near the end?
Sure. Let's see if I have a picture of this. So here's an example of layered 3D display. Okay, known since Disney, maybe even before, repopularized by Ramesh. Okay? And you see different depths of these layers are the shears in phase space, like I'm talking about. Okay? So in this case, you're talking about rays. You can also talk about the statistical properties here to get the angular spread. Right? So in fact, here's an example of the angular spread. So angular spread in the y-axis, and then basically resolution or the spatial modes on the horizontal axis. And you can see you're limited in your angular spread basically by the depth of this, the amount of rays you can control. Okay? So a simple way to extend this is to put a lens there. Right? If you're talking about manipulating the rays or the angular spectrum per point, okay, having a lens here can extend this. Okay? If you want to get even more detailed, you would use a modulator to give it a better wavefront profile. It can. So the question was about non-uniform speed with the flow. It turns out you can compensate for this. In fact, if you just defocus everything, the center of mass stays the same. So you can figure out the speed from your system. Right? You have all the distances and angles. So you can correct for that self-consistently.
All right. So let's thank Jason again.